VC Calc, this is your day 53 notes on trapezoidal approximation. Trapezoidal approximation you'll find at the end of today's lesson is going to be another way in which we can nicely approximate the area under a curve. So before we get into that, of course, we have a warm-up question to look at. Given f prime of x, okay, so here's the derivative, is equal to sine of x squared. Find f of 2 given that f of 1 equals 3. So I'm going to figure out the original function value at 2. Given that we know f of 1 is 3, think about how we evaluate antiderivatives, which is what we're kind of getting at here because we want to find the original function value, and maybe how that would help you to set up that warm-up question. But that's as many hints as I want to give at this point. Let's go ahead and actually move right on to the bottom half of this page where we're going to evaluate 3 different integrals. So here are the 3 integrals we're evaluating. The integral from 0 to 1 of x squared, and then we're going to change the bounds -1 to 0 for x plus 1 squared, and then 5 to 6 of x minus 5 squared. So here's just a visual representation of what each of those areas would look like, right? So for x squared, here's the area from 0 to 1. X plus 1 squared we know is a shift to the left 1 unit, and then there's that area right there. And then if we shift to the right 5 units and take the integral from 5 to 6, that's the area in question. And now that you've seen what this looks like graphically, maybe you already know what conclusion we're headed towards here. But if you're unsure, go ahead and find those integrals. So if I take the antiderivative of x squared, we know that's x cubed over 3. If I plug in my upper and lower bounds, it would be 1/3 minus 0. So the area under the curve, y equals x squared from 0 to 1, is 1/3. Moving on to the middle case, you might want to, just to make your life a little bit easier, you can either expand that and make it x squared plus 2x plus 1, or if you do a u substitution, the nice thing is that du is equal to 1 dx. So if you just think of this as u squared, which would be then u cubed over 3 when you find its antiderivative, since u is x plus 1, the general rule here would be that this would be x plus 1 cubed over 3. And we're going to plug in our bounds of 0 and then -1. When you plug in 0, you get 1/3, because it's going to be 1 cubed over 3. When you plug in -1, the top becomes 0. So this would also be 1/3. Okay, and maybe that's what we thought would happen. But in that last case, I don't think I have to show another u substitution to justify that this antiderivative would be x minus 5 cubed over 3. With our upper and lower bounds of 6 and 5, well, 6 minus 5 is 1. 1 cubed over 3 is 1/3. And plugging in 5, you get 0. So area under that curve is also 1/3, 1/3, 1/3, 1/3. Well, that makes sense. If we're talking about area under a curve, as I shift that curve, left and right here, and I adjust the bounds accordingly, we would expect that the area over that interval should be the exact same for the function y equals x squared. So what that brings us to is some conclusions we can make on the top of the next page. In general, if the function we're integrating is a transformation of a parent function, then we must do the following to the limits of integration. So if you have some transformation and you're integrating from a to b for f of x minus h, and you want to figure out maybe just integrating the original function f of x, what you would do is you would subtract h from each of those bounds in your definite integral, and you could apply those bounds to the original function f of x, and that would be just fine. Or if you have a function f of x, and you're integrating from a to b, and you want to figure out what would be the integral for some transformation f of x minus h, notice how the bounds become a plus h and b plus h. We know in general that for f of x minus h, let's say if it was f of x minus 2, that's going to shift 2 to the right. So because of that shift 2 to the right, we have to add on that value of 2 to both bounds. So just make sure you're kind of careful about that notation there. But hopefully that concept of horizontal translations makes sense. So here's a quick practice with that. Evaluate each of the integrals from 0 to 2 of 3x squared dx. Well, that constant of 3 can just be pulled out front, can it, right? Or you can leave it there, it doesn't really matter. But this is going to wind up becoming, if I up that by 1, it's going to be just x cubed. And we're going to integrate that from 0 to 2. So 2 cubed minus 0 cubed is 8. Okay. So moving on to this one over here, you really have two paths you can take. You can say, oh, okay, well, this is just a transformation of this one over here, isn't it? So we're starting with the transformed version over these bounds. I could say that this is the same thing as the integral of 3x squared dx. And then if I adjust the bounds accordingly, because this is f of x minus 4, and we're getting back to f of x, what do I do with those bounds? Well, you're going to subtract 4 from both of those ends. Okay. So when I subtract 4 from both ends, we're going to get from 0 to 2, which now is actually the same exact integral that I started with over here. So we know the answer should be 8. So if you notice a parent function that's closely related that maybe it would be easier to integrate, then this is a rule that you can apply. Otherwise, a quick u substitution here again would do us pretty good to say if u equals x minus 4, then du equals 1 dx. So if I treat this as 3u squared, the interval is u cubed, but oh wait, u is really x minus 4, so it would be x minus 4 cubed. And when you integrate from those bounds from 6 to 4, you would get 2 cubed minus 0 cubed, which is still 8. So either way around it, whether you use this rule of transformations or you kind of just integrate what's given to you, we're capturing the same amount of area if we shift 4 to the right and then we shift those bounds 4 to the right with it, okay? So just a quick note about integrating with maybe some transformed functions. All right, moving on to the example below it, it says consider the function defined by capital F of x equals. So it's the integral from 1 to x of 2 minus radical t e to the sine t dt. The graph of the integrand is given below. The function f of x is related to the area between the curve and the x-axis. So if we think about what's going on here, if capital F of x is what I want to sketch in the ends, capital F of x is the integral of all of this. So what do I know about all of this right here? If I want to know what is this function in relationship to f of x, this function, 2 minus radical t e to the sine t, this is really f prime of x, isn't it? This is the first derivative. So what we're doing is, given a derivative, we want to find the original function f of x, which we've done curve sketching like that in the past, okay? But that would make sense if I applied the fundamental theorem, right? Take the derivative of both sides. That would plug in an x over here, and this function in terms of x would equal f prime of x then. So what we're going to do is we're going to, on our calculator, make a table of values for x, comma, f of x by typing this exact integral into y1. And what's going to happen is we know that we're going to get accumulated areas. And those accumulated areas represent the y values of the function, f of x. And we'll use some of that information and what this graph looks like here to be able to accurately sketch the curve capital F of x. So I've already done that. If you want to catch up to me, I typed in the integral from 1 to x of 2 minus radical x e to the sine x dx. Okay. Now your calculator is going to think about this for a little while. I'm going to double check that that looks okay. Let's see. We want our table to go from, okay, I think we'll start at a table start of 0 here. But if I go to the table, it's going to think a little while because it's calculating all the area under the curve here, that accumulation as time goes on. So don't be too worried if your calculator is really thinking very hard about this. While my calculator's thinking, I'm going to talk about, oh, nope, never mind. We're ready to sketch. Okay. So because the interval that we're given here is from 0 to 7, that's what I'm going to graph f of x over, is 0 to 7. So at 0, the y value is negative 2.086, which seems to make some sense to me, I guess, if we have kind of the backwards bounds there, that we might have some negative accumulated area. And then at 1, it also should make sense that we're getting 0 when the bounds match. And then at 2, I have 2.028. 3, 4, 5, 6, 7. Okay. And these are all points that I can plot along the way, but I want to think about some other features of f of x based on the graph that this is the derivative. Okay. So at 3, we're at 2.832. 4, we're at 2.943. All right, a couple more to go, 2.898. So we're heading back down now, 6, 2.713, and at 7, 1.993. Okay, so with that data, we're gonna go ahead and start setting up some axes so that we can sketch capital F of X. Okay. If I look at the y values on this curve, it looks like the highest y value is going to get pretty close to 3. So if I'm setting up my axes appropriately here, and the lowest we go is just below -2 for our first coordinate. So we don't have to go that far down on the y-axis. Okay. So some things to think about here is what we know about the graph is if this is the derivative, we know that the graph is increasing for f of x. It's increasing over the interval from 0 to 4 because the derivative is positive over that interval. Once the derivative becomes negative, then we know it's decreasing from 4 to 7. So what does that mean? It means that x equals 4, if we're going from increasing to decreasing, is going to be a relative max. So when I'm trying to accurately create a sketch to represent this, this is really good info to think about. In terms of other accuracy that would be nice to think about, we want to think about concavity. So in thinking about the concavity of the graph of capital F of X, if this is the derivative, we know concavity is dependent on the second derivative. And what we know is that the slope of the tangent lines initially is going to go from positive and then eventually over to negative for the rest of the way. Okay. And we know that this point right here at 1, 0, okay, that's going to be an inflection point for the curve. Because it's the point at which the slopes are going to become positive and then turn over to negative. Okay. So the concavity is that we're concave up from 0 to 1, and then we switch over to concave down from the rest of the interval 1 to 7. And based on where we're increasing, decreasing, concave up, concave down, and these points right here, we should get actually a really nice sketch of what this looks like. So here's 1, 0, 2, 3, 4, something special happens there, 5, 6, 7. Okay, so I may not plot all these points exactly, but 0, -2.086, that seems like a good point to start with. From 0 to x equals 1, we know that we're concave up. So we're going to do this. And then the whole rest of the way, I have to switch over at that inflection point and be concave down. We know that at 4, 2.943, just about 3 up here, that's the max. And then by the time I get to 7, 1.993, so almost 2, that's kind of where this is going to end for our interval. So we're going to come up and curve this way, hit that max, stay concave down until the end of the interval at 7, 1.993. So using the table of values, thinking of these accumulated areas under the curve here as the y values on the function f of x, and knowing that this graph right here, this accumulation function represents the derivative of capital F of X, we can draw a lot of conclusions as to what F of X looks like as far as increasing, decreasing, and concavity. There is a lot of information that we're kind of putting together there. And although we've done curve sketching in other contexts this year, this can be a little tough to kind of wrap your brain around. So if you have questions about this, let me know next time I see you. But otherwise, you'll see other questions come up like this, where you have an accumulation function defined, which means that this is the derivative, and we'll get some more practice with sketching and making some conclusions about this, okay? All right, so let's get into what the title of today's lesson is, which the title of today's lesson is another numerical method And it's going to be the trapezoidal rule. And the trapezoidal rule is useful because if you think about what's going to look like when we draw trapezoids instead of rectangles, it's going to be a nicer fit to the curve. So there are times where rectangles are not the best choice. So why not choose trapezoids? Because if I were to draw a rectangle here, let's say I was going, from some inscribed rectangles. Well, when I draw that height across, there's a lot of area that I'm not capturing. However, sorry, I had to sneeze. It's not happening though. Okay. If I think of these as one of the legs of the trapezoid, you almost want to turn your page this way for a moment. Do you see all these trapezoids that are here? Here are the parallel bases, and then here's one leg, and then here's another. Look how that other leg fits the curve so nicely there. Same thing. Here are the parallel bases. If I connect to this leg over here, there's really not a lot of area that we're missing out on every time I sketch this leg over here to create a trapezoid. Okay, maybe this would be a little bit of an overestimate at the end, but we get the idea that when I draw in these trapezoids, that's going to be a really good approximation for the area under a curve. So how do we develop the rule for finding the area of all these trapezoids? Well, it would be helpful to remember what the area of a trapezoid is in general, which is the height over 2 times the sum of the bases. And what we're going to have to realize in this case is look at where the height is. Look at where that h is. The height is that delta x value right here along the x-axis. Okay, the bases that we're going to be adding up are the function values, those heights along the function. So we have to think of that carefully when we go to start developing the formula that, okay, we're going to take the height over 2, and we're going to do the initial y value plus the other y value, y sub 1 here. Okay, so we're going to add those bases. Plus, then the next trapezoids area would be the height over 2, and then it would be y1 plus y2 now. Okay, so we're going to take this height plus that height for the sum of those bases. And what we'll see as we go down the line and we think about the sum of all those trapezoid areas is that all the, I would say, inner base lengths get doubled, right? Because y1 was a base that I used for this first trapezoid, but it also is a base in the second trapezoid. y2 gets used twice as a base. Gets used once for the second trapezoid and again for the third trapezoid. So in general, when we develop the trapezoid rule, the first base and the last base never get doubled for area purposes, but all the other bases in the middle on the inner part of the interval from A to B will get doubled. Okay. So as we continue our development here, transferring over from our y values to function notation, y sub 0 is what f of a is, and y1 could be found by doing the function value at x sub 1. So then this is f of x sub 1 plus f of x sub 2. And like I said, the only two things that don't get repeated are the height, the base length of the trapezoid at the start of the interval, f of a, and then f of b. But everything else in the middle is going to get doubled because those other heights are shared between two trapezoids. And remember that the way we're calculating the height is it's our delta x, which is the length of the interval divided by n, where n is the number of trapezoids or the number of sub-intervals that we're using. Okay. So with all that being said, why don't we, now that we have the development here, this is what the trapezoidal rule states. Let's practice. So it says use t with n equals 4 to approximate the integral from 1 to 2 of x squared dx. Compare t, capital T, which is what we'll use for the trapezoidal approximation, with the exact value of the integral. So this is an integral that we know how to find, but let's go ahead and sketch it. So we want x squared. I'm going to really exaggerate this here. We want this from 1 to 2. So from 1 to 2. And we want to use 4 trapezoids. Okay. So we need to break this up into 4 subintervals. So we get 1, 2, 3. Okay. So we want to find all of these areas here. 1, 2, 3. Okay. So to get started, what we want to do is figure out, let's develop what the height is, because that height is going to get divided by 2, and then it will be sitting out front as kind of a GCF factored out from everything. So the height is b minus a over n. It's the length of the interval divided by the number of trapezoids that we have. So that's going to be a height of 1/4. Right? So the length of the interval is 1 divided by 4 subintervals. So then when I go to do the trapezoidal rule for T4, remember that your formula is height over 2 times the sum of the bases. So the number out front is going to be 1/8. So just be careful with that, because the formula is h over 2. Okay. So then from there, what am I going to do? I'm going to do the first height right there for that base length at f of 1. That's only going to be accounted for once. But the second base length of the trapezoid at, this would be 1.25, that's going to count in the first trapezoid and the second trapezoid. So it's going to be plus 2 times f of 1.25. And then this height right here counts in trapezoid 2 and trapezoid 3. So it's 2 times f of 1.5. And then f of 1.75 counts twice. But by the time I get to the end of the interval, this base length is only accounted for once for the area from 1 to 2. So then we're just going to put plus f of 2 at the end. And there is my formula for the trapezoidal approximation. So I guess if you want to type this all in at once, you can go to y equals, type in x squared. And then if you want to get fancy, go to the home screen and you can do 1/8 times. How do we do f of 1? You can do alpha trace and do y1 of 1. Plus, then we have 2 times y1 of 1.25. And you can continue with this process, plus 2 times y1 of 1.5, plus 2 times y1 of 1.75. And then at the end, plus, we're not doubling this height anymore. So that's just going to be y1 of 2. Now, clearly, if it's an easy enough function like x squared, you could just put a plus 4 down there if you wanted to. But this should be the correct answer, 2.3475. The area under the curve using trapezoids is 2.34375. All right. Well, since we know the value for the definite integral, we can find this without using trapezoids. So let's just compare and see how close we were. The integral from 1 to 2 of x squared dx would be x cubed over 3 from 1 to 2. So 2 cubed is going to be 8/3 minus 1/3, which is 7/3. And 7/3 is 2.3 repeating. So we're pretty close, aren't we? 2.34375, pretty close to 2.3 repeating. In fact, we can calculate the error real quick by taking what we have, 2.34375, subtract the actual, and then divide by the actual, and we'll see that the error is, so minus 7/3 divided by 7/3 to get 0.00446. So there's approximately a 0.45% error in using a trapezoidal approximation. That's pretty good. There's not a lot of error there when it's a less than 1% error using trapezoids as opposed to finding the exact value for our definite integral. Well, the last thing that I want you to do is, and I'll let you try this on your own, compare this to what we know with RAM. So use your calculator to use 4 rectangles and calculate LRAM, MRAM, and RRAM. And once you get those 3 answers, I want you to calculate the error within those 3 answers and compare the error to what we had for trapezoids, okay? So next time I see you, we'll go over that information real quick. We'll figure out what the RAM approximations are and then see if the error is pretty close to what we have for the error for trapezoids, not so close, and how we feel about using rectangles as opposed to using trapezoids, okay? So that's the general idea for today, this new trapezoidal rule. You'll see a lot of questions come up like this on the homework. So next time I see you, a little bit more practice with trapezoids and some calculator work. Have a great day.